Okay, we can see that working with in the vertical direction just brings in a gravitational pull of acceleration of minus 10 meters per second squared. So we're going to include that with our problems that we have. And so in the really good chart, we'll have, because it's downward, minus 10 meters per second squared. And here's a problem. It says a water balloon is dropped from a hotel balcony 45 meters above the parking lot. The time it takes the balloon to hit the ground and the speed just before it hits the ground. So find the time it takes the balloon to hit the ground. We should add that. And the speed just before it hits the ground. Okay, let's pause and copy that down. So we'll get out a really good chart here. Put that on there. And we can fill in some information. Let's draw a little picture over here too. Water balloon is dropped from a hotel balcony. So there it drops and it falls downward. Each second it covers more distance because it's moving faster over each successive second. The total distance that it falls is 45 meters. And it says dropped. What do you think that means? Right. The initial velocity is 0 meters per second. Okay, so now because it's going down like that, our distance is going to be negative, and we can fill right away, we can put in the acceleration is minus 10 meters per second squared. We also know VI is 0. Okay, when we look at that now, we could start solving to fill in the chart, and if we fill in the chart, we'll answer the speed just before it hits the ground. That will be VF. And since it's speed, even though it's negative, we'll put in the positive because it's just speed. It doesn't have a direction associated with it. And it also asks for the time, so that will come up here because that will be the elapsed time since it fell. Now this is one of those problems where we have the acceleration and the distance and the initial velocity, and we're going to use one of our longer equations to get VF in this case. So nice thing about this one is the VI just cancels right off. Oops. And you get VF squared, because VI is 0, 2 times minus 10 meters per second squared times a minus 45 meters. So VF squared equals 20 times 45, which is 900 meters squared per second squared. And then square rooting both sides, we get 30. Now, this is an interesting point because you have to, it's actually plus or minus 30, isn't it? That would solve that equation because minus 30 squared is also 900. So which one is it? Well, since it's going in the downward direction, we know that this VF here is minus 30 meters per second because it's going downward. The speed, though, is 30 meters per second for that part there. The average is that divided by 2 minus 15. The delta V is VF minus VI, which is minus 30. And now at the time we can get from a couple of different equations now, but let's use this one. Solving that for delta t, you would bring up the delta t, and then you would divide out the a, You could put in numbers if you wanted, but gives it to us in the formula form. The delta V was minus 30 meters per second, and A was minus 10 meters per second squared. So that gives you 3 seconds. It takes 3 seconds to fall that 45 meters. And you solve both parts of this problem. It's going to reach the ground before it bursts. It's going to be going 30 meters per second, and the time will be 3 seconds. Here's another problem. If I can get this off, I don't know. It's reacting slowly, but at any rate, take some time to copy this down. Michael threw the ball up 5.2 meters. Mr. Ring caught it at a speed of 0. What speed did the ball leave Michael's hand? Well, the ball was being thrown up to a point up here, caught it at 0 meters per second up at this point, and it went up 5.2 meters. So now we can get a really good chart. We can plug that stuff in for it. We don't know what VI is, but we know what VF is. It's 0 meters per second. We also know that it goes up a height of positive 5.2 meters, but A is still minus 10 meters per second squared. Now, we asked for what speed did the ball leave Michael's hand. So this is actually what we're looking for. And now we would use some of our equations to figure this out. We have A, we have VF, we have delta S. So we could once again use the equation we used in the last problem. That's what just comes right into my head. But this time VF is 0. So we would get minus VI squared, because that would be 0 bringing it over. And we'd have VI squared equals 2 times minus 10 meters per second squared times 5.2 meters. So this is actually supposed to be positive here. I made a mistake. So we still have the minus over here, and then that goes away. 2 times 10 times 5.2 is 104. It could be positive or negative once you take the square root. Both would solve it, but in this case, since it's going up, it would be plus 10.2 meters per second. And of course, in the actual question, it asks for the speed, so that's all we needed. And so we actually solved the problem we would be done. Well, this is 10.2. So the average would be 5.1. This would be minus 10.2 meters per second, VF minus VI, and delta T would be 1.02 seconds to fill in the rest of the chart. Well, this sounds kind of like a horrible problem of cruel and unusual treatment to somebody that happened, but true. And it says that a newspaper article a few years back said that a woman, while watering her plants, fell out of her apartment window a distance of 22 meters and landed on an aluminum air conditioning housing, crushing it to a depth of 54 centimeters. She then got up and walked back to her apartment, fully analyzed. So she lived through that, partly because of the crushing of, or actually mainly because of the crushing of the air conditioning housing. And that give was enough to allow her to get back up and walk back to her apartment. And 22 meters is a lot, especially when you think it's about 5.5 from our classroom down to the base of the sidewalk. So multiply it by close to 4, you can see it's quite a distance. So we'll start by analyzing her fall. So she falls out a distance of 22 meters. So that would be minus 22 meters here. And assuming she just fell, she would start at 0 meters per second. And she's under the influence of gravity once she leaves that ledge, and it's minus 10 meters per second squared. And now we go back to our VF squared equation here. Square root can be plus or minus, but in this case we're going to go with the minus, which is coming down. And the square root of 440 is 20.97 or 21 meters per second. So well, minus, right? Which makes the average minus 10.5, the change of VF minus VI, and our delta T, delta V over delta or over A, which is 2.1 seconds. Okay, so we see that she was going 21 meters per second when she hit that air conditioning unit. So let's get a second chart for that, and we'll analyze the crushing now of that. We know her speed coming in was 21 meters per second, and negative going down, right? And that's going to go, she's going to stop, so that's going to go to 0. And we were also told that it was crushed 54 centimeters, which is 0.54 meters, and that is also negative because it's, right? Yes. Negative 0.54 meters, and A is minus 10 meters per second squared. So the average is the same average as before, same average velocity as before, except we do it in much less time. So, and the change is 0 minus a minus, so this would be plus 21. That doesn't make sense. Okay, so the acceleration is at minus 10. It's not, she's getting stopped by the casing. So that makes, it's not minus 10. It's first off, it's upward because the casing is stopping her. So we have plus 21 meters per second. So let's get delta T from V bar is delta S over delta T. So delta T equals delta S over V bar, which would be minus 0.54 meters over minus 10.5 meters per second. You can see it's quite small. Of 0.05 seconds. Now we can get our acceleration. That's the interesting part of this anyways. Delta V over delta T, 21 meters per second divided by 0.05 seconds. It's 420 meters per second squared. Quite an acceleration, but a lot less than if it was a block of pavement. So, all right, one more problem. You can write it down. A squishy pear is fired straight up from the edge of a cliff, of a 100-meter tall cliff with a speed of 30 meters per second. With what speed does the pear hit the ground? So we're considering this going straight up and straight down, but the pear is shot up and goes down. The cliff here is 100 meters tall, and the initial speed is 30 meters per second. So we can analyze this actually to break it up and do up and down, or you could do the whole thing. For us, let's just do the whole thing. So because it takes in, if you do the positive and negatives, it should work out. So we take off with a plus 30 meters per second. We have the same acceleration. It's always minus 10 meters per second squared. And the height is going to be, say, if we take the starting point as 0, we'll have a height of minus 100 meters. Okay? So now, so with that, we could do, again, our VF squared equation. It's 53.9 meters per second, and since it's going down, we'll be looking at the negative. But it asks for speed, so the speed would be just 53.9 meters per second. Okay? And then the same way to do the averages and stuff, but I'm not going to fill those in now. But you could do up and down as well. So we'll just look at that real quick with a double chart. Is that what I wanted? Well, no. That's for next unit. We'll just use a single chart. We'll add a row on. So when we go up, we start up with 30 meters per second. But since we're going to go up to the top, we're going to stop there. We don't know how high we go. We just know if we were shot up at 100, and we know this is minus 10, so let's fill in what we can. Average, 15. Delta V, minus 30. Delta T, 3 seconds. So now we can get delta S is V bar times delta T, or 45 meters. So now I know if it went up 45 meters, it's going to fall 145 meters back down, because the cliff's 145 meters tall. I know I'm starting at 0 meters per second. I'm trying to find this VF, and I know it's under the influence of gravity. And, well, use this formula again. Oh, it's 2,900 again. Imagine that. And then square root of that, or 53.9, going down, so it's going to be the minus. But we want the speed. So we just have the same speed as before. Okay.